Quantum computers hold immense promise. They could one day solve problems that are impossible for even the most powerful supercomputers of today. These problems span fields like medicine, materials, science, and artificial intelligence. However, building a useful quantum computer is incredibly difficult. The fundamental units of these machines, known as qubits, are extremely fragile. They are highly susceptible to errors from their environment and from the very controls we use to operate them. This constant barrage of noise is one of the biggest roadblocks in the field of quantum computing. It limits our ability to run long, complex calculations. One of the most troublesome types of errors is known as a coherent error. Unlike random noise, which is unpredictable, coherent errors are systematic and repeatable. Imagine trying to draw a straight line with a ruler that is slightly bent. Every line you draw will have the same curve. In a quantum computation, these systematic errors accumulate with every step or every gate operation. They steadily push the quantum state away from the correct answer. This accumulation of errors severely limits what is called the circuit depth, which is the number of operations we can perform before the results become meaningless noise. This challenge has defined the current era of quantum computing, often called the noisy intermediate scale quantum era. We have processors with a few dozen to a few hundred qubits, but they are too noisy to perform fault-tolerant computations. Researchers have been working tirelessly on ways to manage this noise. The ultimate goal is full quantum error correction, a complex process that uses many physical qubits to create one nearly perfect logical qubit. However, that solution requires a massive number of high-quality qubits, far more than we have today. We need a solution for the here and now. This brings us to a recent breakthrough from Google Quantum AI. They have demonstrated a powerful new technique on their advanced Willow quantum processor. This technique, called quantum echoes, offers a way to directly cancel out those damaging coherent errors. It acts like a clever trick that rewinds the effect of systematic flaws in our control system. This development doesn't solve all the problems of quantum computing at once, but it represents a significant step forward. It allows us to push the boundaries of what is possible with today's noisy quantum hardware, bringing us closer to unlocking their true potential. The solution proposed by Google introduces two key components. Encore mi chingi onponi Willow quantum processor, quantum echoes algorithm. Willow is a new generation of superconducting quantum chip, engineered for higher performance. It features enhanced connectivity between qubits and advanced designs to reduce crosstalk. Think of it as a finely tuned instrument built to minimize flaws. This hardware gives a more stable, controllable platform for delicate maneuvers. The processor is a major step forward for quantum hardware. The real star is the quantum echoes algorithm. It's a software trick that manipulates quantum states to undo errors. The idea is elegant, like a sound echo. If you shout in a canyon, the sound travels and hits a wall. It returns to you. Quantum echoes does something similar with computation. It runs operations forward, lets systematic errors accumulate, applies a special refocusing pulse. A reverse sequence follows, causing errors to cancel, like an echo returning to its source. Coherent errors limit the complexity of quantum algorithms we can run. The solution is the combination of the advanced Willow processor and the clever quantum echoes algorithm. The impact is a dramatic improvement in computational accuracy. That lets us run deeper, more meaningful circuits on NASQ-era machines. For the future of computing, drug discovery, financial modeling, this matters. Better quantum computers bring us closer to solving currently intractable real-world problems. This is a practical step toward making quantum computing useful. In this essay, we take a deep dive into the breakthrough. First, explore Willo's architecture and why it's superior. Then, unpack the quantum echoes technique and its analogy. Next, see how this improves on existing error mitigation. Finally, examine broader implications, new applications, and research directions enabled by this hardware-software combo. This work clears a path toward fault-tolerant quantum computation. At the very heart of the Willow processor are its fundamental components, the qubits. A qubit, or quantum bit, is the basic unit of quantum information. While a classical bit can only be a zero, a qubit can exist in a state of zero or a combination of both at the same time. This property, known as superposition, is what gives quantum computers their immense potential power. Willow uses a specific type of qubit called a transmon. These are tiny, artificial circuits made from superconducting materials. When cooled to near absolute zero, these circuits behave like artificial atoms with distinct energy levels we label 0 and 1. To understand a transmon qubit in simple terms, imagine a pendulum that can only swing at specific fixed heights. The lowest height represents the zero state. The next height up represents the one state. The quantum magic happens when we put the pendulum into a superposition, swinging at both heights simultaneously. The Willow processor refines these superconducting circuits to be more stable and easier to control. The quality of these basic building blocks is the foundation upon which all else is built. Better transmons mean a better quantum computer. The entire Willow chip, a small intricate wafer of qubits, must be run in an extreme environment. To keep their fragile quantum properties, the qubits must be kept incredibly cold. This is done with a dilution refrigerator that cools the processor to about 15 millikelvin, colder than deep space, and just a tiny fraction above absolute zero. This cryogenic environment protects qubits from thermal noise, the random jiggling of atoms, which would destroy the quantum information. This extreme cold is only one part of the control system. To manipulate qubits, to put them into superposition, or entangle them, researchers use precisely timed microwave pulses. Those pulses are generated by sophisticated custom-built electronics and sent down carefully engineered wires into the refrigerator. Each pulse is shaped with nanosecond precision to nudge the qubit between states or to perform a quantum gate. Willow combines extreme cold, high-frequency electronics and advanced circuit design to create a controllable quantum environment. A quantum computer's power doesn't just come from individual qubits in superposition. It comes from their ability to work together. This collective behavior is enabled by entanglement, a strange connection where the fate of two or more qubits becomes linked. To create entanglement and run complex algorithms, qubits must be able to interact with each other. This is where the processor's connectivity comes into play. In early designs, a qubit might only be able to talk to its two immediate neighbors. Willow features a significantly enhanced connectivity, where each qubit can interact with a greater number of other qubits on the chip. This is a critical design feature. Think of it like a social network. If each person can only talk to the two people standing next to them, information has to travel slowly and awkwardly through the crowd. If each person has direct lines of communication to many others, complex conversations and collaborations can happen much more efficiently. In a quantum processor, higher connectivity allows for the more direct execution of multi-qubit operations. This reduces the number of steps needed for complex algorithms, which in turn reduces the opportunities for errors to creep in. It makes the processor a more flexible and powerful computational tool. To manage these interactions, Willow incorporates a crucial piece of technology, tunable couplers. A coupler is a small circuit component that sits between two qubits and acts like a controllable switch. It also acts like a dimmer. It allows researchers to turn the interaction between two qubits on with high precision. It allows researchers to turn the interaction between two qubits off with high precision. When a 2-qubit gate needs to be performed, the coupler is turned on, allowing the qubits to become entangled. When they need to be isolated, the coupler is turned off, preventing them from influencing each other. This level of dynamic control is essential for performing high-quality quantum operations without unwanted side effects. The ability to tune these couplers is what makes them so powerful. Instead of being a simple on-off switch, their strength can be adjusted. This allows scientists to precisely moderate the interaction strength to optimize the speed. This allows scientists to precisely moderate the interaction strength to optimize the fidelity. It also helps to completely zero out the interaction when it's not wanted, mitigating a common source of error known as residual coupling. This fine-grained control over how and when qubits talk to each other is a sophisticated feature of the Willow architecture, enabling cleaner and more reliable computations than were possible with previous generations of processors. Section 3. Engineering for precision, crosstalk and control. In the densely packed environment of a quantum chip, one of the biggest engineering challenges is crosstalk. This is interference. An operation for one qubit unintentionally affects neighbors. Imagine whispering a secret in a quiet, crowded room. People nearby overhear. When a microwave pulse controls one qubit, some energy can leak and disturb adjacent qubits, introducing errors. These unwanted interactions are a major source of infidelity, corrupting delicate quantum states. The Willow processor design includes advanced measures to combat crosstalk. Meticulous physical layout of qubits, careful routing of control lines, integration of on-chip shielding elements, engineering the geometry precisely, using materials that absorb stray electromagnetic fields, like building better soundproofing between rooms. Reducing crosstalk ensures the whole qubit system can operate in parallel without interference. Ultimately, the goal of these architectural improvements is high-fidelity gates, better transmons, enhanced connectivity, tunable couplers, reduced crosstalk. A gate is a fundamental quantum operation, flipping a qubit from 0 to 1, entangling two qubits. Gate fidelity measures how perfectly an operation is performed. 100% fidelity means flawless operation. 99.9% fidelity, sound 1% chance of error. Small errors accumulate over thousands or millions of gates. Willow pushes single qubit gate fidelities very high. Willow pushes 2-qubit gate fidelities very high. This requires a holistic approach, advanced hardware design, sophisticated software for calibration and control. Automated routines constantly measure chip performance. Automated routines fine-tune control pulses to compensate tiny drifts. This pursuit of higher fidelity turns noisy components into a device that can surpass classical computers. The Willow architecture provides a precise foundation for the next step, using software tricks like quantum echoes,